Hello everybody, welcome to Blue Marble Science. This is part 2 of the testing and measurements of the universal gravitational constant using the Cavendish device. So you guys grab some popcorn and your favorite beverage and we'll go through this thing. We did a summary of all the testing in part 1, so I won't go through that in detail again, but just as a reminder, the first test series consisted of 14 tests, and they were all conducted with the 22 kilogram large mass and 330 gram small masses, and they all used a .007 diameter steel torsion wire, a guitar string in actuality. Now we've done a second series of tests, and this time we have 16 tests. These were conducted again with the 22 kilogram large masses, but this time with the larger 780 gram small masses and 2 different torsion wires. One is a .008 diameter beryllium copper wire and the other is a .007 diameter tungsten wire. So those are the 2 test series that we'll take a look at. Now you recall before that we talked about random error sources, and random errors occur in every experiment. These are things that just happen, well, randomly. And they may appear in some tests and not appear in other tests because they're just random in nature. What we need to do is understand that they have an effect and then do what we need to do to mitigate or minimize that effect. So again, this was talked about in part 1. We're not going to go over this in detail. Just to let you know, though, that these things have been considered and every step possible was taken to control these things. Systematic errors, though, are another thing. These are errors that are constantly present in the experiment, and they're things that you can take into account because they're always there. Cavendish identified 6 different possible systematic errors. The first is an oscillation time correction due to the mass of the balance beam itself. Again, we talked about this in part 1. The second error that Cavendish identified was the gravitational attraction of the balance beam itself. That's just the little lightweight wooden part, and it really has no effect whatsoever. The third error that Cavendish talked about was the reverse attraction to those distant small masses. Now that is an error that needs to be accounted for, and we have done that. The fourth potential error that Cavendish mentioned was the attraction of the brass hanger rods. He found that they had no effect, and I ran a similar test, and I agree they have no effect. The fifth error identified by Cavendish is the attraction of the case itself, and again he found that to be negligible, and I agree with him. And finally, Cavendish identified the influence of the position of the masses on the oscillation period. Now we noticed that, we noted it, we measured it, and it is mitigated simply by making measurements of the time period with the masses in their resting positions, not in a neutral position. So all of that has been taken into consideration, and it results in 2 corrections. One for the oscillation period correction due to the mass of the beam itself, and you see those here on the screen. Secondly, a correction for the reverse attraction to that small mass that is distant from the large mass. So you'll see these factors included in the spreadsheets that follow. Now let's talk about data collection and analysis. Of course, we can always do it the old-fashioned way, and I've got books full of this stuff, folks. But thanks to modern technology, I've also got about 600 gigabytes of video. So I can always go back, watch the video, and use what you see on the screen and write down some numbers. That makes it a little bit easier. But there's an even easier way of doing it, and that's through the use of a nice little piece of software known as Tracker. This is a video tracking software. And when you use this in combination with a time-lapse video, you get a very nice graph of the oscillation. And it's quite easy then to go back and pick out the peaks and the exact values associated with those peaks. To demonstrate tracker for you, I've loaded the time-lapse data from April the 18th into tracker, and that's the video you see sitting here. I've calibrated tracker. I've given it 200 millimeters from the 100 millimeter mark up to 300 millimeters, so it knows what that linear distance is. And I've given it an origin back here at 100 millimeters also. So every X measurement that tracker makes is going to be referenced to this origin. Now I've also selected the very left side of the laser spot, right about there, as the point tracker should look for in each of the frames. And now all we have to do is tell tracker to search. And away we go. It's an amazing piece of software. It does an extremely nice job. And it's going frame by frame, finding that left side of the laser spot, measuring that offset distance from the origin, and plotting it down here in this table. So you see it as in real time here as it's retrieving that data. Now this runs on for a few minutes. We go through a number of periods of oscillation, and then you're going to see the point where I actually move the large masses, and you're going to see the reaction of the laser here on tracker. You'll see it, you'll see the sinusoidal oscillation move upscale right there. And now the masses are on the other side, and the oscillation simply continues. So we're going to let this thing run through to the end, and then we'll see if we can make a measurement of the oscillation period. Still got a little ways to go. You can see where it is down here on this slider. That's the end point right there. So it's almost there. Just got a few more frames to go. And we're done. So in this table, we have the time in seconds. And you'll notice that each one is 20 seconds apart. And that was the frame rate that we used for the time lapse. So let's go back. We've got 1, 2, 3, 4, 5, 6, 7. We can go 1, 2, 3, 4, 5, 6 periods and figure out the time from what tracker collected here. Let's put our pointer back there. And now what we want to look for here in the X displacement is a maximum. And there we have 119.1 at 6100. So write down 6100. Now let's go back to this peak, this extreme point here. And again, we want to find the maximum value, and here we go to 133.2. We've got two of them, 133.2 and 133.2. One at 300 seconds, one at 320. So let's call it 310. 6100 minus 310 will be 5,790 seconds. If we divide that by 6, we'll get the period of oscillation. I'll be right back. 5790 divided by 6 is 965 seconds. And that's how we can make measurements with tracker. We can take the data in multiple methods, ranging from real-time data collection, as Cavendish did it, and that is a total pain in the neck, trust me. Or we can video record the experiment and then go back and retrieve these extreme positions. Or we can use software like Tracker. But the objective, of course, is to find the resting points with the masses in alternate positions. That change in displacement is what allows us to calculate the value of the gravitational constant. So now we need a method of finding the resting point. And there are a couple of ways of doing this. Now this is another plot of the April 18th data taken by Tracker. And one thing that we could do is just simply wait for the balance to stabilize in each of the resting points, but that's a very time-consuming process. An alternate method is the method that Cavendish used. Cavendish measured 3 successive extremes. You need at least 3, but you can have more than that. Cavendish would measure an extreme at position A and average that with the extreme at position C, and then take that average and average it with the extreme at position B. And that's what you see in the little formula I put down. Now if you look at the spreadsheet on the right, from the actual data collected on 4/18, we had an extreme of 280, a second extreme of 176 on the other side, and another extreme at 272. If we average 280 and 272, we get 276. We average that 276 with 176, and you get 226. But we can move down now and take the next 3 if we'd like, and average 176 with 181, and then average that with 272. At the end of the day, we can end up with a very accurate estimation of the resting point without ever having to allow the balance to completely come to a rest. And that's the number you see there. Notice that it's very close to the original first 3 extreme points that we used. And that's usually what I've found. You're rarely off by more than, say, 0.2 of a millimeter. This is how most of the data has been analyzed. Now let's talk about the test results we have to date. This was the first series of tests. Through 14 tests, we obtained an average for the gravitational constant of 6.63 times 10 to the minus 11th. And that's only about 0.7% below the published value. That's quite a good result. I was very happy with that. Now let's see if we came close to that with the second series of tests. And this is that data. This time we have 16 total tests. The first 3 are with a beryllium copper torsion element, and the last 13 are with the tungsten torsion element. Here's how those tests averaged out. Series 2 came up with 6.62 times 10 to the minus 11th, a little bit below what we had in Series 1, but still only about 0.83% lower than the published value, so very consistent with what we measured in the first series of tests. If we look at the combined total, the test average is 6.62 times 10 to the minus 11th. The standard deviation is 3.2 times 10 to the minus 12th, and we have a 95% confidence interval of 1.15 times 10 to the minus 12th. Our error is about 0.77% lower than the published actual value for the gravitational constant. Now that's very consistent with what Cavendish measured, and that was the objective. And, at this point we could just call it a day and say, okay, we're done. But I still think we've got a little work left, and I'll tell you why. You'll recall early on that we measured the mass of the large balls to be 22.03 kilograms, but we did that with a very inexpensive electronic scale. Now, while I trust that scale for the purpose it was used for, which was just to ensure that both the masses were the same or the same within about 20 grams of each other, the absolute value of that number I don't trust. I've made measurements of the actual average diameter of those lead balls, and it would appear that they are probably more like 22.4 kilograms. So I believe that needs to be addressed, and I'll be making a video on this. But the best way I have of doing it will be a volumetric measurement using a displacement can. In other words, we'll just simply measure how much water one of those balls displaces, and once we have that volume, we know the density of lead very, very accurately, so we can get a very accurate estimation of what the actual mass is. What are we going to do next? Well, as I just said, we're going to verify the mass of those large weights. I want to repeat one final series of tests using all of the equipment and wizardry we have at our disposal, tools like tracker and so forth. So when that's over, we'll analyze and publish the final results. And then there's one more thing to do, and that's to take Cavendish to his new home. I'm not going to tell you where that's going to be quite yet, but I think you guys will be happy with it. Hey, thanks for watching, and I really thank everyone for their support through this. It's been a long journey, but we're getting close to the end of it now. Hey guys, don't forget to hit the like and subscribe buttons down there. Shout out to the patrons and PayPals and to everyone who has supported this project from the beginning. It is really appreciated. With that, I'll catch you guys on the next one.